The concept of human-powered flight dates back centuries, but the modern pursuit of human-powered aircraft (HPA) began in the mid-20th century. One notable milestone in the history of human-powered flight is the Creamer Prize, established in 1959 by British industrialist Henry Creamer. The prize was created to encourage the development of human-powered aircraft capable of completing a figure-eight course around to markers spaced half a mile apart. In 1977, American engineer Paul Macready's Gossamer Condor won the Creamer Prize by completing this challenge. Macready later went on to develop the Gossamer Albatross, which famously crossed the English Channel in 1979, becoming the first human-powered aircraft to do so. Since then, human-powered flight has continued to be an area of interest for engineers and aviation enthusiasts, with ongoing advancements in materials, aerodynamics, and human performance pushing the boundaries of what's possible. Today, human-powered aircraft are used for various purposes, including recreation, research, and competition. Building a human-powered aircraft (HPA) involves several steps, from design and construction to testing and piloting. Conceptual design: define the purpose of the aircraft, for example, recreational flight, competition, research. Establish design requirements, including payload capacity, range, speed, and aerodynamic performance. Conduct preliminary research on existing HPAs and aerodynamic principles. Detailed design: develop detailed specifications for the aircraft, including dimensions, materials, and propulsion system. Use computer-aided design (CAD) software to create a 3D model of the aircraft. Optimize the design for weight reduction, aerodynamic efficiency, and structural integrity. Materials and components: select lightweight, high-strength materials for the airframe, such as carbon fiber, fiberglass, or lightweight metals. Source or fabricate components, such as wings, fuselage, tail, and landing gear according to the design specifications. Design and integrate the human-powered propulsion system, typically consisting of pedals and a drivetrain connected to the aircraft's propeller. Optimize the gearing ratio to achieve the desired thrust-to-effort ratio. Construction: assemble the airframe and components according to the detailed design. Use techniques such as bonding, riveting, and welding to join structural elements. Ensure proper balance and alignment of the aircraft to optimize aerodynamic performance. Testing and optimization: conduct ground tests to evaluate the aircraft's structural integrity, stability, and handling characteristics. Perform wind tunnel tests or computational fluid dynamics (CFD) simulations to refine the aerodynamic design. Conduct flight tests in a controlled environment to assess performance and make necessary adjustments. Pilot training: provide training for the pilot to operate the aircraft safely and efficiently. Practice takeoff, flight maneuvers, and landing procedures under various conditions. Flight operations: conduct test flights to validate the aircraft's performance and capabilities. Collect data on flight parameters such as airspeed, altitude, and endurance. Iterate on the design based on test results and pilot feedback to improve performance and efficiency. Throughout the process, it's essential to prioritize safety and adhere to relevant regulations and standards governing aircraft design and operation. Collaboration among engineers, pilots, and other stakeholders is crucial for the success of the project. Typically have strict limitations on payload capacity and endurance due to the constraints of human power. This restricts their practical use for transportation or cargo delivery. Weather sensitivity: human-powered flight is highly sensitive to weather conditions, including wind speed, direction, and turbulence. Adverse weather can significantly affect the aircraft's stability and control, increasing the risk of accidents. Piloting a human-powered aircraft requires significant physical exertion, leading to fatigue over extended flight durations. Fatigue can impair the pilot's cognitive abilities and decision-making, potentially compromising safety. Structural integrity: HPAs must be designed and constructed to withstand the stresses of flight while remaining lightweight for efficient propulsion. Structural failures or material fatigue could lead to in-flight emergencies or accidents, typically limited to specific operating conditions, such as calm weather, smooth terrain for takeoff and landing, and controlled airspace. These limitations restrict their practical utility and may require specialized infrastructure for operation. Collision risk. Human-powered aircraft share airspace with other aircraft, including powered airplanes, helicopters, and drones. Collisions or near misses pose a significant risk to HPA pilots, especially in congested airspace or near airports. Human-powered aircraft must comply with aviation regulations and safety standards established by civil aviation authorities. Failure to meet these requirements could result in legal repercussions or restrictions on operation. Thanks for watching. Please subscribe, like, and share.
Can't see the end, but we'll see it through. Dangerous times, don't fly too high. Be sure to keep the ground in sight.